minus sign. That minus sign hopefully cancels that minus sign. Put a plus sign over there. Okay? But do I still get things right? Mu hz let me see. Let's open here. hz. So if I multiply by epsilon, I seem to get an equation that looks something like this. This is the funny equation. Okay, so this equation can be rewritten in a different forms. That okay, it can be written in this form by first extracting mu epsilon z from the outside and then multiply by mu inverse or mu again. If I multiply this equation by mu, okay, if I multiply this whole equation by mu, okay, and then take this mu hz outside and obtain the second equation that I have written below. Okay, so this is the equation that I have intended to arrive at, and the reason why I've intended to arrive at this equation is because if you look at the structure of this equation, it's no different from the one that we have derived from, or for EY. The equation that we have derived for EY looks something like this. So this is the equation that we have derived a little while ago, and this is the equation that we have derived for hz. And we say that hz characterizes TE wave. This is the equation for TE wave. So is this equation. This is also an equation for TE wave. And they look mathematically very similar, except that this one more operates on mu hz, this one operates on EY. But this equation, we make an assumption in this derivation that there's no y variation in the problem. We're assuming that the electric field points in the y direction. E is y. But this one, we make no assumption. We just assume that hz is not equal to 0. That should be the characterization of the TE wave. We arrive at this equation. And this Laplacian transverse is equal to this thing over here. Okay? And if in fact there's no y variation in the problem, this equation will reduce to that equation. But this equation it's not predicated on the fact that there shouldn't be y variation. So the electric field can be polarized in the y direction, it can polarize in x direction, in any direction, and it's valid for all kinds of TE waves. Okay? So this is a more general equation for TE waves. And then, of course, by the same token, you can arrive at the equation for TM wave by duality principle. It should be, if I apply or invoke duality, I would have this as my equation. This is a square here. Epsilon Ez equal to 0. Okay? For TM wave, Ez is not equal to 0. So I have this as my equation to characterize TM waves. So are there any questions so far regarding the derivation of these fundamental equations for TE and TM wave? Yes, Aditya?
If there is no assumption that in this derivation which we did, then why we do the previous derivation?
What is that?
There is no assumption in this, right?
Right.
But there is some assumption in that.
Right.
So then why did we do that?
Why did we do that? Well, this is, I thought, easier to understand. Right? You have a wave polarized in the y direction, it has to be a TE wave. And if it's the only field component for the electric field, then you arrive at the fact that this must be 0. And then you started out with the vector wave equation and arrive at this quite easily. But then to arrive at this takes a bit of doing, more work. Okay, you have to assume that only H3 components exist in the field. If it's only H3 component, it must correspond to a TE wave. And if that is the case, the H3 component has to satisfy this equation. And this equation must be the equation for TE wave. By the same token, this is the equation for TM wave. Okay? But this is more general but harder to derive. Okay, with the help of you all, I derived them anyhow. Right? I fumbled and made some mistakes, but then I finally was able to arrive at them. Okay? So if we have mu inhomogeneity and epsilon inhomogeneity as a function of V, like a layered medium, this inhomogeneity can be arbitrary. We need only to solve these two equations for TE and TM waves. And what is more important is that the boundary conditions must be embedded in these equations as well. Remember how I was trying to convince you that boundary conditions are actually part of the partial differential equation. So if you write down your partial differential equations correctly, the boundary conditions are also embedded in them. So we don't have to worry about what boundary conditions to impose. If you specify epsilon to be a function of z, mu to be a function of z, boundary conditions will automatically emerge in your solution. This is something perhaps not realized by many people. You say, oh, when you have two regions, a problem with the interface, epsilon 1, epsilon 2, epsilon 3. When you solve this numerically, we have to derive a numerical solution for this region, numerical solution for this region, numerical solution for this region, match boundary. You don't have to. You derive a numerical method that's valid for all three regions. And then your boundary conditions will automatically be satisfied at the interface. Okay? So, let's see how we can solve these problems and how we can eyeball this equation and conclude what boundary conditions there should be when we solve this. So, for this simple case over here, I say this is a simple case. Okay? Then it only involves partial squared, partial x squared. Not equal to 0 for simple case. Then I will conclude that my EY must be something of this form, EY e to the I kxx, something of this form, right? It can be plus or minus I kxx. If something involves partial square partial x squared in this simple fashion, this must be the simple case, okay? And then similarly, I can say the same thing for hy. Hy must be something of this form. The x dependence must be very simple, okay? And then I can break a problem into regions. And then if I substitute this back into this PDE, partial squared partial x squared must be minus kx squared. If I substitute this back into this PDE, and I conclude that my EY can be a function of z e to the plus or minus ikxx. My EY must be a solution to this ordinary differential equation, mu ddz, mu inverse ddz plus omega squared mu epsilon minus kx squared. EY, z must be equal to 0. This must be true just by direct substitution. You will to substitute this in here, partial square partial x squared becomes minus kx squared. And this is a simplified equation. And this now becomes an ODE because there's no more partial square partial x squared. And similarly, you can show that this is true for the Tm waves. Okay? So PDEs now become ODEs. And so if you have an interface, say epsilon 1, mu 1, epsilon 2, mu 2, you can eyeball this equation and actually arrive at what the boundary condition should be right at the interface. Okay? You don't have to go back to Maxwell's equations. Boundary conditions are embedded in this equation. So this is a function of z. And let's assume that this is z equal to 0 here. Okay? By eyeballing this equation, I immediately see that E1y must be E2y at z equal to 0 at this interface. Right? This must be true, because if this has not been true, what will happen to partial z? This statement is saying that if I were to plot my EY as a function of z, it must look something like this. It has to be continuous at z equal to 0. If it had not been continuous there, what will happen to partial z? You have a delta function there, right? And if your delta function there, this is regular, this is not infinite. If you differentiate it another time, you have a doublet. But there's nothing in this equation that you can have to cancel a doublet. So a doublet cannot exist. So just by eyeballing this equation, this must be true. If this is true, when you differentiate it once, okay, then the most you can get is the EY dz. The most you can get is that you have a step discontinuity. And then hopefully this will compensate for the step discontinuity, and we differentiate the second time around, there's no delta function emerging. So this is at least one of the boundary conditions, but from the second part of the equation, you can also conclude that this must be true. That mu1 inverse partial z of E1y must be mu2 inverse partial z of E2y at z equal to 0. If this had not been true, it means that this will have a step discontinuity, and if you differentiate, you will produce a delta function. There could not be a delta function in this equation. There could not be such a singularity. So by just eyeballing this equation, you arrive at these two boundary conditions. So I teach you how to arrive at boundary conditions just by eyeballing the equations. No need to go through very complicated derivations. And you can do that in many parts of solving Maxwell's equation. Just staring at the equation, you know what the boundary conditions are. You don't have to go through the nitty-gritty details. So you get the same thing for HY2. These are for the Tn waves, and then you will have epsilon 1 inverse partial part of the H1y. Let's go to epsilon 2 H2y. X z equal to 0. Okay. So are there any questions regarding these boundary conditions?
Yeah, I have a question.
Yes.
So you said EY has to be continuous, but in your EY, your first EY, you have this little pointy thing, and when you differentiate that, you still get some sort of thing. But you're saying that the first one you can compensate for with U inverse, but the second one you can't. Why is that? Even though they're both kind of like the derivative is not, it's not smooth at 0.
Yeah, this has a jump discontinuity, right? And mu can have a jump discontinuity too. So mu inverse can compensate for this jump discontinuity so that the second derivative is continuous. So I'm just showing you a hypothetical case where this mu1 and mu2 is not the same. If mu1 and mu2 are the same, the slopes will be the same. So I would have drawn this picture differently. The first picture, if I draw them, I would have drawn them like that. The slope is continuous. But mu1 and mu2 are different, and the slopes are different. This is the picture corresponding to mu1 and mu2 are different. Okay, but it satisfies this boundary condition.
Okay, but if you let EY have the discontinuity, the set discontinuity, and then you take the partial, what do you get, and why can't you balance that out?
Well, if this had looked like that, if this had looked like that, this is EY. You differentiate it once, it produces a delta function. You cannot compensate the delta function with something that's regular and finite. You differentiate it another time, you get the W. So this is an impossibility. This is not possible. So you rule that out. Okay? Let's take a 5 minutes break and then we come back and talk about this further.